So we are now coming to the chapter 7, and we'll go into the power flow studies. Here you can see a view of the sub-chapters for this chapter, and I really want to highlight the section, this 7.4 and 7.5, which is the Gauss-Seidel power flow and the Newton-Raphson power flow. Those are the two main strategies to solve the power flow in this course. We have older also, you probably heard maybe before, but there's something called the fast decoupled power flow here. So it's simpler methods where you can more decouple the equations. And but I think we will start with the 7.3, the power flow problem. And then this 7.1 and 7.2 is more like background you can read on your own, but it's more on the actual development of the algorithms. But we want to, I think I'll start with the 7.3 and go through some examples there. When you start on the load flow problem, I think you should start with the two-port equations. And here you can see like two buses or two nodes. The bus 1 here and bus 2 here, represented with a voltage, length and angle for 1 and 2. And then you have a load flow, or we can have a current, you have an impedance, and then you have, of course, a flow on the other side, and you don't know actually which way this will flow before we do some calculations. So we have two ports, and you can then write like a simple expression for this. Remember that often we use this bus 2 as a 0 degree, as a reference angle, when we do calculation. So if we have then an expression for the current equal V1 and let's see, minus V2, then we put 0 degree, and then we have the impedance below, the theta angle, and we can express, now we got 0 here, oh, it removed itself. Then we have this expression, V1 on set, or not set 1, we can erase this one, let's see, let's take it again. Set, and then we have the let's see, delta minus theta, and then we have minus sign between V2 on the impedance, like this. So this will be then the expression for the currents over between these two buses. However, now we can, of course, more look on the flow or load, and we know that the let's take this one, the S1 can be expressed as the V1 times the current, complex conjugated. So we have an expression for the current, and we can actually write it down here, P1 plus J Q1 equals, we get V1 squared divided on impedance, and get E theta minus V1 V2 divided on set. I just used the expression over here and multiplied actually just by V1. So you see it came V1 in both expression here. And the angle like here, theta plus delta, like this. So here you have an expression for the load flow 1 here. So here you can see what it's actually representing in this equation. Now we get a term with the V1 voltage in square here. And then we get a combination with V1 and V2 and the other. In the same way we can also do for the S2 on the second bus. We can have now it's V2 times current in complex conjugated. It will give an expression as V2 squared divided on ZE that angle, and then we have minus V1 V2 on Z in theta minus delta. So the difference now is that we have a minus here, and you can of course also see that we have a V2 square now, not V1, when we are working at the bus 2. Further, you can then express this as active power, P1. If you take the P1 now, then we just take the expression we had previously, and we just make cosine for it. So V1 squared equals cosine of theta and minus V1, sorry about that, V2 divided on impedance Z. And then we have cos theta plus delta. So that is then just for the P1. Then you can have for Q1, you can have for P2, and you can have to Q2 for the second bus. So in the same expression, and actually when we have all the 4 equations, I'll give you that in a handout. We can actually see that we will have 9 variables. When you have all together, we have actually 4 coupled equations. That means that 5 variables need to be defined because we have only 4 equations. And typically known is that we have the impedance of the line. We also have P2, Q2, and V1. So they are typically known. And of course, the set also have the angle also in it. So since we have 4 couple equation, we have then 5 variables that must be defined. These equations are also what we call the loss, no loss 2-port equations. And we typically have a relationship defined that theta equals the pi divided by 2 minus alpha. And alpha is typically what we call a loss angle. And if alpha is 0, that means that the r in the line is 0. This is something we typically define in the equations to actually simplify it even more. And remember also that if you have 90 degrees on this angle here, so the cosine becomes 0 here. So that is important, and the whole expression then moves out. So here we can see the overview of all the equations, as I said. This document I'll put out in Canvas. So here you can see the S1, S2, just we are using V and not U. Then you have for the P1 equation, you can see here, P2, Q1, Q2. So you see that becomes minus sign here when you're working with the second bus. And you also become square here in the U2 and U1. So it's a 4 coupled equations, and it's 9 variables, so we need to specify 5 of them. Another way that you already have worked with is the voltage drop method. And yeah, we can start first maybe on this one. So the line model. So we can do some simplifications and have really easy expression that can help us a lot. So here we have this line model, and you can see, for example, in this first voltage here is U1 down here to the left. Remember now that we have, here's bus 1 and bus 2. It can also be typically G and L, generator load bus, also S, sending and receiving, sending and receiving. So you will see a mix of those. So yeah, you just have to keep track of it. So for example, here now I mixed a little bit, but if you can see U1 here now to the left here is then the same as the VG in this feature. So you see that this U2 here will then be the same as VL. So the voltage, the total voltage of this vector will be this vector U2 or VL plus Ri cosine to phi, and this will be, you can take another color, this will be this vector, and this is this here, let's see, this one, and then we will have plus xy sine to phi, and that is this length here, as you can see here. So then you see we will have we are come to this point here, and then plus in the complex format we will have up here, we will have xi cosine to phi minus Ri sinus to phi. And if you see, this is the whole, let's take green maybe, here, down here, that's the xi cosine to phi. Then you take minus here, this one, to come to final the whole trigonometric here. Of course, here is already done some simplification that we can express it like this, and then you will have like a voltage drop, as you see here, will then be representative the drop over the resistance and the reactance in the line here. Here you can see we have used another angle instead of theta as I had earlier, but you just need to keep track of it. There's different notations when we move along. So this is the voltage drop method, and we will now see more on the how we can get the simplified expression as I just showed you. So we know now this equation here representing these vectors as I just showed you. You can of course insert powers here, and you can get an expression as you see here, inserting it down those into that equation, and you will have this relationship. And what we're actually doing is actually neglecting this term, this side here, thinking that the angle here between is very little. So, and then we can get actually even a further simple expression as you see here. I'm jumping now actually directly to chapter 7.6, which is not actually the main emphasis, but I think it's important for you to that this can give a clear picture of how the flow is and what they are like interacting with the flow of the active power and reactive power. So for a transmission network, we typically can say that the X of the line is much larger than the resistance. So, but this is, however, not in a lower voltage grid system, because when we have cables, we have much more larger R's resistance. But in transmission network, we can say this. So now you can also see that we have the S here, sending. In the start of this lecture, I was using 1. So just try to keep track on the sending and receiving. And one more thing, maybe we should go here first. This is a feature of 7.15 in the book. So here you have the sending. Let's see this one here, and then the receiving here. So as I said earlier, we have voltage times the current complex conjugate, and you can get this expression. It's the same as I did before, just with a different notation. And now also we have a sign here, and this you should is just to remember that this is because of this loss angle. It's depending on how we defined it, because when I had it in equations, we have the cosine here. So this is due then to this, the theta I said is equal to the pi half minus so-called loss angle. So that means we can represent with the 90 degrees here, and because of some trigonometric function, we can get represented as the sine here, and then it becomes sine here and cosine here. I will come back to that when we develop the equation for the Newton-Raphson method and Gauss-Seidel. So this is important to remember. And as I said earlier, we can then express actually with some simplification this and this. When we know, we can actually how the load is related to different R and X in the system. See, as you see now, the R is gone, and now we can see that the sending power here is related to the angle difference here. So, and this is very important, and one of the fundamental ideas is that active power is very strongly connected to the angle difference, while reactive power is very strongly connected to the voltage difference the length of the vectors. So these are two very important things I wanted to show you before we start on the Gauss-Seidel and Newton-Raphson. If you were confused about this approximation here, it's just that typically this angle difference is less than 10%. So we can just neglect the sign and just use the angle difference. That is good enough. And also we know that these angles here can be approximated to 1. This is also good enough just to see how the flow is varying. If you're doing like small hand calculations, this can be very useful. So by this, when you will not go much deeper into the decoupled power flow, but now we can maybe understand more. Those two equations are decoupled, so we can actually do our own load flow analysis for the active power and one for reactive power. It makes computational effort much smaller and faster in speed.